When we first started our lesson on nuclear chemistry, we talked about how much energy was in a nuclear reaction. Far, far greater energy than in any chemical reaction. So the question is, where is that energy coming from? We know the potential energy change as electrons are gained, lost, shared in a chemical bond. That causes changes of energy. But where is the energy coming from for these nuclear reactions? Well, we need to define something called the nuclear binding energy. It's the energy required to break up a nucleus into its component protons and neutrons. So if you started off with, for example, a helium atom, which consists of 2 protons, 2 neutrons in the nucleus, the energy it takes to pull that apart into its individual protons and neutrons is the nuclear binding energy. Now, what is of interest to me and this argument of where the energy is coming from is the mass of the nucleus is always less than the sum of the mass of the protons and the neutrons that make them up. So if we were to look at a helium nucleus, for example, it would have 2 protons, and we'll draw them in solid, and 2 neutrons that make it up. Okay, so 2 protons, 2 neutrons, that's a helium nucleus. If we were to pull that apart, and it would take a lot of energy to do so, into 2 protons and 2 neutrons that were not held together, the mass of this part, the mass here, is always less than the mass of this part. So there's a loss of mass that's going on there, or a gain of mass, whichever way you want to go with it. And that is where that energy is going to come from. Okay? So let's continue with that argument. We would expect a fluorine isotope, fluorine-19, to weigh exactly the same as 9 hydrogen atoms. Well, what's in the 9 hydrogen atoms? It has 1 proton plus 1 electron. Okay, so that would be 9 hydrogen atoms, and then 10 neutrons. That is what a fluorine atom consists of. The 9 hydrogen atoms gives you all the electrons you need, all the protons and the neutrons. Well, this is not what we find. Here is the mass of 9 hydrogen atoms plus 10 neutrons. But here is the mass of a fluorine atom. We see that there is a difference in those two. This difference is called the mass defect. So let's calculate this mass defect in this situation. It would be 19.15708 minus 18.9984, and that would give us a difference of 0.1587. That's to 4 decimal places, which is all we can really know. Okay, so that is the mass defect for fluorine-19. Now this is in units of AMU, atomic mass units, or as our book now uses, just a U. So what happens to this mass? Where'd it go? What's it used for? How is it playing a part in this? Well, that mass is converted to energy, and it's this energy that's needed to hold that nucleus together. So what do you mean mass is converted to energy? Well, we know from Einstein that E equals mc squared. Okay, energy is mass times the speed of light squared. So if we're talking about mass defect, we'll do it in terms of delta. Delta E is the difference between the energy of, and delta is always final minus initial, products minus reactants. Let's think of it this way: the energy of the pieces minus the energy of the whole, come here you, whole nucleus. Okay, that would be the difference in energy coming from this. I was saying energy. This is the mass of the pieces minus the mass of the whole nucleus. In other words, in the case of our fluorine-19, our mass defect was 0.1587 AMUs. And if you put that AMU in here and put the speed of light in here, which is 3 times 10 to the 8th meters per second, you could determine how much energy is required or getting converted, how much mass is getting converted to energy in this process. Now, I went ahead and did the work on this, and I not only put in these values, my 0.1587 and my speed of light, but I also did some unit conversion, and I ended up for a single atom to have a energy defect of 2.4 times 10 to the minus 11 joules per fluorine atom. Or if you did it per nucleon, which we're going to talk about here in just a minute, if I were to convert that per nucleon, there are 19 nucleons in a fluorine atom, and that ends up giving us 1.3 times 10 to the minus 12 joules per nucleon. So that's the energy required to pull it apart. If I wanted to take fluorine and pull it apart into its individual, I would have to apply that much energy total, or this much energy for every nucleon that I want to pull off. Now, if it requires energy for them to be pulled apart, it would release energy when they come together. Now, each element has its own unique energy per nucleon. Now, fluorine was kind of, this is a weird unit, mega electron volts. But what I found was with the mega electron volts is that we are about 8 for fluorine, and fluorine is probably this guy right here, I'm going to guess. It is 19, right? So it's right before 20. So this is it for fluorine. It's about 8 mega electron volts per nucleon. Each element has its own unique per nucleon. Now, for a big heavy atom, let's say we're talking krypton with 36 protons and more than twice that neutrons, we would have a different full binding energy, but when you calculate it per nucleon, it would probably be somewhere in the magnitude of, let's see, 83 krypton is in this range right here, so this might be about where krypton is. So each element has got its own unique binding energy per nucleon. This is a way that we can compare them all, even though they have different number of nucleons. Now, up here at the top where you see that pink box, these are the elements with the highest nuclear binding energy per nucleon. They require the most energy to pull apart. This is telling me that they are the most stable of all the isotopes. Okay, they are the most stable because they have the most energy per nucleon to pull them apart, meaning they would release the most energy per nucleon when they get formed. Now, your lighter elements down here, your hydrogen, your helium, as they undergo fusion, they end up moving in the direction of more stable isotopes, and they have a release of energy. So nuclear fusion releases energy. Elements that are heavier don't have as much energy per nucleon, and as they undergo nuclear fission, meaning splitting, they are going to be moving towards more and more stable. So this is a driving force for both fusion and fission, is being pushed towards isotopes that have a greater binding energy per nucleon. And so as these reactions, a small amount can generate a very, very large amount of energy. You do not have to calculate nuclear binding energy per nucleon. You do not have to take mass effect into calculations for this class. But you need to understand what the driving force is for obtaining energy from light elements with fusion that come together to form more stable and release large amounts of energy, or nuclear fission, where as they break apart into a more stable isotope, they will release vast amounts of energy.